All right, good afternoon. Clearly I have a branding issue. I should have called it review session if I wanted anyone to show up, I guess. But yeah, I'm here. Any questions for the three of us that are here? Because that's all this is. I'm just here. I'm not piling on new content. It's not a ruse or anything. It's just questions about anything in the course so far. Feel free to ask. Sorry? Oh, you four exams before this one? Yeah, this one's the 24th. Okay, so it's low in the priority list. All right, well, no questions, because I'll just be here then. It's been good, I think, hopefully. Sweet. Yeah, it's an applicable course, but unfortunately, I tried to make it so that you guys hopefully picked up some actual useful skills from the course. Because when I took it, I don't even remember anything that happened in it. And then I relearned the stuff on my own later. I'm like, wow, this is actually useful. Yeah, I'm hoping to add more and change them into exercises and just give you guys some solutions to it because, yeah, some of it I would rather people actually learn from reading good code as opposed to just kind of making stuff up. But it's nice to try it too, but yeah. Hello. Do you have any questions?
No, not really.
Okay. So,
Oh, it's just office hours.
yeah, it's just open office hours or reviewer if you want me to go over anything or whatever. This is unplanned, no new material time.
Oh, okay. Yeah, I haven't started going over everything, so that's not a good sign, is it?
Not particularly. Hello.
Like the haircut.
Oh, thanks. Yeah. I mean, we can also, let's see here. We can also look at the topic list if you want that as inspiration. Let's see. So here's stuff we have learned. So this is, again, yeah. Okay. So, yeah, so the question just for this is what's the difference between a mutex and a spin lock? So a mutex is like a general lock that lets you just have mutual exclusion. And it could be any type of implementation. And a spin lock is a specific implementation of a mutex. So a spin lock specifically doesn't have a queue or anything. So if it doesn't acquire the lock, it'll just try over and over again. And sometimes you want that implementation because it's really, really responsive. So as soon as it's unlocked, you get the lock immediately. And sometimes like the critical section's really, really small because the default mutex implementation uses a queue and it'll put the thread to sleep if it can't acquire the lock and then wake it up again in some random amount of time or maybe when another thread unlocks it. So it has a queue, it has a bunch more overhead. So if it's a really small thing, you want to use a spin lock. But it's an actual implementation, and sometimes you might actually care. All right. Any inspiration questions from the first 12 lectures. Hopefully that spurs everyone's memory. Quick, rapid fire. How do you create a process? Sweet. What do you need to do when you create a process after you create it? Wait for it. Yeah, you have to acknowledge your children. Don't want any orphans, don't want any zombies. Everyone knows what those two are? Hopefully. Let's see. That was wow, we took 3 lectures to go over that? Wow. Yes. So the question is, can a process be both an orphan and a zombie? And the answer to that is yes. So you can make a child and then your child terminates. You don't call wait, so it's a zombie. And then the parent process just terminates, calls exit. And then that process is now an orphan and a zombie at the same time. It would get reparented probably to a nit, and then a nit would wait on it, and then it would just die. Yeah, you can also have just an orphan, just a zombie, or just a process running that's not terminated yet. So yeah, they can be both. They're not mutually exclusive. Basic IPC, let's see. That was read and write. You're just reading bytes and writing bytes and reading bytes from a file descriptor. I don't think there's probably any questions about that. Yeah.
I probably missed this, but I remember on the midterm there was a question about doing like a bunch of reads or one big read.
Yeah.
I wasn't really sure what the difference would be between the two.
Oh, okay. So back in lecture 2, the kernel mode thing, remember there's that system call interface between you and the kernel? And if you make a system call, it's actually much, 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 much slower than just calling a normal function, because your CPU has to change modes. It has to go into kernel mode, then the kernel has to know what you're doing, and then actually do whatever you asked it to, and then do that. So there's a lot of system calls are really, really slow. So the question on the midterm was like 1,000 something system calls versus just one, and you would always want the just one. So there's like a specific stream of research too that tries to speed up the system call interface by like batching calls together. So instead of doing like, 5 system calls, they try and just make one system call that does all 5 things. So that's like one kind of flavor of the research that's out there for that. But yeah, you can write a paper just on implementing that. And then there's like the kernel architectures, which we didn't really go into because we didn't really implement a kernel. We kind of saw it the last bit, like adding some code to the Linux kernel, but there's those different architectures, right? The monolithic kernel that has everything in it. So you need to do a bunch of, or the idea behind that is you don't do as many system calls because the kernel does everything. So like all the drivers are in kernel mode, all the file systems are in kernel mode and everything. While if you have a microkernel, the idea behind that is to have kernel mode do the least amount of work possible. And then your file systems would all have to go through system calls to actually work. And all the drivers would be like normal programs, and they would have to use system calls too. So that's like, and like, there's a line between them. So like on Mac, they don't let you write kernel code because they're Apple. So all Apple drivers are like user mode stuff. So you just write a driver and then you ask the kernel, hey, this is my driver for this, please run it, and it runs as a normal process. So you can't ruin any hardware or like touch anything. And I think the Windows drivers are actually in kernel mode, which probably explains why Windows, or at least did, crash a lot. And like, well, Windows 98 was probably before any of you were born, so. Pipes? So what about pipes? So pipes, if you create a pipe, you can think of it as like a buffer that's managed by the kernel. And the interface it gives you are just two file descriptors, one to write and one to read, and that's it.
So if you have a process that's reading and like a process that's writing,
Yeah.
and like they run in the order so that the reader is like trying to read first, will it like wait for the other guy to write?
Yeah, so, whoops, dog. Let's go. So if you, let's say we make some process. You can see that, right? Okay, yeah. We make some process, say it makes a pipe, right? Say it makes a pipe, and then file descriptor 3 is the read end, and file descriptor 4 is the write end. So without even forking or anything, that process can use that pipe and read and write to it if it really wants to. It's kind of useless because you're communicating to yourself, but you could do that. And yeah, if there's nothing in the pipe, so you can think of a pipe as just being like some buffer over here. It will make sure that you don't have any invalid reads or anything like that. So if nothing's written to it and there's nothing currently in the buffer and you call read on it, read is what we called a blocking system call. So if there's nothing to read, it'll just not return from read and actually block your process. So your process won't wake up until there's actually something there to read, and then it would return from that.
So if something like writes twice,
Yep.
the other one reads once,
Yeah.
it will only read like the first thing, it can't write.
Yeah, so the question is if, let's say we forked, here, let's fork. Boom, we forked. This is now process 3. And let's say that process 2, you said it just writes once or writes twice?
Like writes twice.
Writes twice. Let's see, we'll write, whoops, to 4. Something like that. So, and then this one just calls read from 3 with, let's say we just have like a big buffer. And this buffer would be in that process, like it would be its own array, right? So let's say we make a buffer, that's the size of a page, and we read to the buffer. So the question is, what would the other process read? Well, we actually don't know, because remember, all these system calls, they return the number of bytes read. So because it needs to read something to the buffer, but you don't know when it returns from read if the buffer just looks like this. Like it just, process 2 could finish writing high, and then because there's something in the buffer, this could wake up, like the scheduler could say, okay, you can go now, return from wait, or return from read, and then the read would actually say, hey, I read 2 bytes, and it would put high in that buffer. Another possibility is process 2 does both the writes. So in here, we would get high by, and then after process 2 does both the writes, then process 3 wakes up, calls read, and it would actually read, it would actually read high by, which would be like 5 bytes. So we actually don't know. It's like the same thing with threads. You don't know when you'll get interrupted or whatever, because processes are like threads, right? The OS schedules them whenever it wants. So you'd either see hi, bye, and that's probably your two possibilities. Yeah. Question is read and write atomic, and the answer to that is yes. They're supposed to be thread safe because the kernel is supposed to be managing a whole bunch of different things. So everything the kernel does is thread safe. For the most part. There might be some weird caveats with that where you have to like read the documentation, but for the most part, they aim everything to be thread safe and process safe too. So because two processes could be calling read on that as well, and they'll be atomic.
If you did read like 2 bytes and then read 3, would you always get the first one very high?
Oh, yeah. So let's say if you instead of doing the one read, you did it with this and you said how many bytes you want to read, like this. Yeah, so in that case, the first one would definitely return hi and the other one would definitely return bye, minus any errors that could happen. So if, that, yeah, in this case, there should be no errors unless, yeah, there should be no errors under normal behavior, but you might get like, when we introduced signals, we saw that sometimes a read system call can be interrupted. So the read system call might be interrupted or something weird, but under normal conditions, it'll always work.
So if you just put the buffer in like a for loop, like one read, then like you'll be stuck in the for loop, right? Because it'll always just get near the buffer and just send that.
Yeah, like if you have a read and a for loop, we did that, right? So if we go, let's see. Okay, please track me. So all the way back in 6. So that was essentially our CAD implementation, right? There's just a while loop that just read over and over again. So it would read over and over again while there's still data to read from standard in. And the only way it exits is if read returns 0, which means there's no possible way to get any more input. So that, like, this was the implementation for cat, essentially, right? All it did was read from standard in and write whatever it read out to standard out. So yeah, you can just read over and over again, and if it's a pipe, the read end will report closed if there's no write ends open for any process. So it's not possible to get any more data into the buffer. So if it's not possible to get any more data into the buffer and you've read everything in the buffer, then you're done. So there's no possible way to get more data, and that's how it knows it's done. So that's why, for the example 2, when we started screwing with pipes, sometimes if we didn't close the right end of the pipes, it would just kind of sit there and look like it's stuck. It'll look kind of like it's deadlocked, I guess, and that it doesn't respond to anything. But that was because you forgot to close one of the right ends of the pipe, so it was reading from a pipe, and it was still possible to get data in there, even though it wasn't, you never wrote anything there, and it just sits there forever.
So can like multiple processes write to the same pipe?
Yep, multiple processes can write to the same pipe.
And can they like read the same pipe, or can only like one of them read?
Yeah, they can all read the same pipe too. But remember that file descriptor, when we talked about the file descriptor table, it has a position in it. So it's atomic, like the question before. So if a bunch of processes try and read from them, it's guaranteed that only one will read whatever that data is, and then that process would advance the position, and then the next one that reads would get the next chunk of data. So if you have like, yeah, so here, let's go back to this. So if, instead if I had, whoa, took too much. So let's say instead of these reads, say I had the reads in different processes. Something like that. Well, then it's kind of like a race condition between there. Like the reads are going to atomically happen, but you don't know which one's going to read first. So in this case, here, let's simplify it. Let's just say that this writes hi bye all at once. So this just writes hi bye all at once, and then both processes are reading from that file descriptor. You don't know which one's going to go first, right? And where that buffer wants to read from starts here, like that's where the internal position would be in the like global open file table. So either one could return from read. So this one could return first. It would read hi, which would be the first two characters, and then atomically it would adjust the buffer, so this is the next thing to read. And then the other process would return from read, and it would see, and it would read bye. But what's the other option? Huh? Hit, yeah. Yeah, the other option would be if process 4 went first, and because the reads are atomic, they're guaranteed to read everything because of how we have it set up, but you don't know what in order. So if process 4 returns from read first, it would read hib, and then process 3 would read ye. So, and that's the same if you like shared a file descriptor and then forked like 8 times and then each called read. Well, you're guaranteed that across all the processes calling read, you'll read the entire thing, but you have no idea what the order is going to be. And that might be a very poor idea, especially if you assume that like each process is the only one reading from it and it represents a whole file or something like that. Then each process would get different chunks of a file if you're unlucky, and then you probably won't be able to read it.
What happens if you like close the read end of a pipe?
Oh, so if you close the read end to a pipe and that's all the read ends, like all the read ends are closed, and then you try to write to it, the kernel will give you an error on that write system call. So yeah, it'll return -1 set error no, and I think there's an error no that says pipe closed or file descriptor closed or something like that. But there's a specific error for that.
Is that the same as if you read from a pipe that you can't write?
If you read from a pipe that doesn't have any writers, then it will just say it's closed if you've read everything.
Does that just return 0?
Yeah, that just returns 0. And that's like, if it was a file, read would return 0 if it reached the end of file, and read returning 0 for a pipe just means no more data. It's essentially done.
Okay.
Yeah. Yeah, too bad I wrote this exam like a week ago. Otherwise, I could have put that in. Well, there's always next time. All right, any other things, or should we go back to the list of topics? All right. So let's see. So after that, what did we get? We got virtual memory. Is that cut? Oh, that's cut off a little bit. Yeah, virtual memory, everyone's favorite topic. So hopefully Lab 5 drilled that into you a bit better. So other people didn't have Lab 5, but so hopefully you do much better at the virtual memory question. Oh yeah, virtual memory page table implementation, those three, that was all virtual memory lectures. You did the tricky thing about page tables is implementing copy on write. That was like probably one of the harder things you could do. So hopefully that wasn't too bad and you didn't just, hopefully you didn't just slam in code until all the test cases passed. But sometimes people do that. Let's see, threads. So threads, kind of hard. So any questions about threads? Well, threads themselves aren't that hard. Databases are hard. So everyone, off the top of your head, what's a data race? Yeah, so that's a fine enough definition. When there's a bunch of things trying to read and write at the same time, more than one, and at least one of them's a write. So the actual word is like if there's concurrent accesses, but same deal. If you have threads, you have concurrency, so you don't really need to say that part. So that's pretty much the concern whenever you have threads. You want to worry about data races because you will get really, really, really odd values, and it will be absolutely a pain to debug. So those are the types of bugs that have lived in the kernel for like 7 years before someone has fixed them. So yeah, that should tell you about how hard they are to identify. And unfortunately for all of you, you are now in the age of multi-core machines. So if you want your program to run fast, well, guess what? You have to use threads. And then you have to worry about it. So if you care about performance at all, you will have to deal with it. And this is why people can't use Python for everything as much as they would like to. So has anyone, okay, who here has ever tried to use threads in Python? One, how was it?
It was all right, I think.
Was it slow?
Yeah.
Okay, so do you know why it was slow? Okay, so Python does support threads, but it's really, 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 really slow. Why is that? So Python is an interpreter. It doesn't actually have compiled code or anything. So within the Python interpreter, guess what? There's a bunch of potential data races that it has to prevent. So the Python interpreter ideally, the Python interpreter would just have a bunch of locks for anything to prevent deadlock. But the easiest thing to do, which is what they did, is they just put a lock around the entire interpreter. So they don't have to worry about any data races. But whenever you call into like the Python interpreter, there's something called the GIL, or the global interpreter lock, and the whole thing locks. So if you use Python and you use threads in Python, it will probably be mostly the same as single-threaded because it's all going to use the interpreter. It just has one big lock around it, so it will only actually use one thread. So it'll be slow as hell. So if you want Python to go fast and you want to stay in Python, the recommendation is to use another process. So there's that multi-process module. So instead of dealing with threading and doing locks, you just use multi-process, which will fork, and then everyone has its own independent copy of the Python interpreter, and they can run at full speed. Well, full Python speed, which isn't that fast. But if you want to make Python go fast, you pretty much need to use processes, which is, hey, good thing we had this course. So, yeah, yep.
So if you use multiple threads, you can't ever exit zero in your thread, right? That just kills everything.
So if you have multiple threads, a thread can call exit 0, and that just ends the process.
So you should exit thread.
Yeah, pthread exit or something like that if you don't want to kill the process.
Okay.
So yeah. If you want to end a thread, it's just pthread exit if you're using pthreads.
And then if a thread like reaches the end of its function,
Yep.
does it pthread exit automatically?
Yep.
Okay.
Yeah, so the question is if a thread makes it to the end of its run function, does it pthread exit automatically? And yeah, it does exactly what you did in lab 3. So if it makes it to the end, it implicitly calls pthread exit, which is what you guys did too, right? So you kind of know how they would have implemented it. Let's see, threads. Wow, we talked a lot about threads. Threads and locks. Center 4 is locking. Oh, we even did a parallelization example. That was fun. So, yeah, but the whole thing is pretty much you have to, A, prevent data races. Then if you have multiple locks, you have to, B, prevent deadlocks. And then in some programs, you also have to, C, ensure some type of ordering between threads, depending on if you have a bunch of dependencies or whatever. All right, any other general questions about threads or anything like that? Okay. Let's see. So last third of the course was pretty much not that much. So it was disks. So SSDs being kind of weird that they have to erase like huge, oh God, I even forget the name. What are they called? Not pages, above pages, whole blocks. Did they call them blocks? They might call them blocks. But you have to erase multiple pages at a time, and you can only write to a freshly erased page, and it has a bunch of weird rules, which is why it makes it kind of difficult. Then we saw file systems, like some basic ones you could do, different allocation strategies. That's pretty much all file systems' job is to give you a name to refer to a file and allocate some blocks in some manner. And all the inode ones, well, you got to see an inode file system up close and personal in Lab 6. So that was a whole file system. So if you're running Linux, the file system you're actually running probably it's just an extension of that, has some more features, but that's essentially all it is. So it's just, instead of being 1 megabyte, yours is hopefully several hundred gigabytes or terabytes. So, but it's the only difference. It's otherwise exactly the same. Then we saw sockets. That was more IPC. That was mostly to give you some background so you can connect to the internet and fun stuff like that. Page replacement, that had the clock algorithm. Hopefully that was okay to follow. You know for sure that, well, okay, well, you can probably deduce that that's on the final, so practice that. That hopefully is free marks. Then general memory allocation, buddy and slab allocators, and virtual machines. And then that was it for the content. Then after that, we saw a fun memory mapping thing, people making machine learning models go fast by knowing about operating systems. Then some kernel module, just so we could see some kernel mode stuff. Rust, which was just fun, I guess. And it was just rewriting that that bank simulator and showing that it prevents data races but does not prevent deadlocks. And then, yeah, today, open office hours. So anything for the last third of the course? The last third of the course was definitely a lot lighter than the rest of it.
In Lab 6, what is the difference between the sibling and the file?
What? Sorry, what do you mean?
I understand what the symbols mean.
Oh, so what the difference between the symlink and the file was? Or here, we'll go here. Okay, so we'll try and flip back and forth because this is probably a good question. So let's say we make a file called a.txt. So it's just a normal file. It gets its own inode, everything right, has no content. Let's make some content for it. Okay. So now it has some content. It's 10 bytes. It's got this inode number, right? So if we make a hard link, oops. So if we make a hard link, refers to the same inode, and it's just another another entry in that directory, because the directories essentially just pair name to inode. So if I modify one of these files, it modifies the same underlying inode. So if I go ahead and I modify this, and then I look at b.txt, well, I see the same contents of the file. All right, and let's make another file called c.txt. And then we'll make a soft link. All right, so we made a soft link. So a soft link does not refer to the same inode. So this is the inode for c.txt, and then it's different than the inode for d.txt because it's supposed to just refer to a different name, right? So it means if I try and access d.txt, it would say, okay, to access d.txt, actually look at c.txt, and then you could read c.txt, right? So sorry, what's your question about symlinks? Like, why would I use them, or?
Yeah, like how is D different from
How is D different than what? Sorry?
well, like I guess then D, like if you delete like A, you would still exist.
Yeah.
The difference.
Yeah. So here. So yeah. So the difference is kind of in their use. So the symlink, it's its own inode, and it just refers like name to name. It has a bit of a hop. So you can think of soft links as name to name, but in actuality, you know what they are. They're name in a directory to inode soft, or to a soft link inode, and that stores the name. So there's like a bit of a jump, but really abstractly, they're just name to name. And yeah, why they would be different? Well, so in this example right now, a.txt refers to the same thing as b.txt, and then c is the same as d, but it's just through another, it's more indirect, right? But if I do cat a.txt, it says I get the same thing as b.txt, and then if I do c.txt and d.txt, they're the same thing, right? Kind of looks like they serve the same purpose. But yeah, so the difference is, well, because it's a hard link, if I do, say I remove a.txt, right? I don't actually remove that inode because there's still something pointing to it, b.txt. But let's say I make a new a.txt. So let's say this is version 2. So now, because I just removed a.txt and made a new one, well, guess what? So if I look at a.txt, this is version 2. If I look at b.txt, it's still pointing to the old one. So maybe you want that behavior, in which case you'd use a hard link. But if you actually want them to always refer to the same thing, then a soft link's probably a better idea because, well, what happens? If I remove c.txt, well, now d.txt refers to c.txt, which doesn't exist, which that makes sense. c.txt doesn't exist. But if I went ahead and made c.txt and said this is v2 of c.txt, well, guess what? Now they both refer to the same thing still, and I didn't have to update anything. Right? d.txt and c.txt are the same thing because I just went through one layer of indirection. I said, okay, d.txt should refer to the same thing as c.txt at all times, so you don't have to play with the inodes or whatever. The final inode you arrive at is whatever inode c.txt arrives at. So it always keeps it up to date, and sometimes you really, really want this. So like a bunch of the times in Linux configuration files or server files or when you have to do cloud stuff, this is how it knows what to start up. So it will just have a soft link that is in a particular spot, and they just say, I don't care, this web server always goes to this symlink and will just start running whatever that points to. And that way, if you update it later, make it point to a different inode, it doesn't care, it just goes to that name and then whatever that refers to. So if you have to update anything, it always stays consistent. Otherwise, if you really wanted A and B to always point to the same thing, that would be really, really annoying. So if you change what either of them point to, you have to make sure to change them all so they all agree. So instead of dealing with that headache, you just use a soft link instead. Yep.
I think you answered this, but d.txt has its own inode, which then points to c.txt.
Yeah.
Which has its inode that points to.
Yeah, d.txt would have its own inode, so you created like a soft link inode, and then the data that's stored on that soft link inode is the name.
So how does D know which directory to find?
So it just uses that name and just restarts the path resolution. So like, because I'm currently in this directory, it would use this current directory. So it's c.txt in this current directory. So I could also do like, for soft links, I could do like this, right? So I could create a soft link that's name is like an entire path. And then, hey, guess what? If I cd to home dir, well, it keeps track of, like my shell will keep track of the paths, but guess what? This is actually my home directory. And it's the same thing as if I went to home John, whoops, like it's the same contents. So it's kind of like a shortcut, yeah.
If you were to cd dot dot there after you cd to home dir through this soft link, it would have brought you back to where you were initially.
Here, let's see, what do I call it? Open office. Yeah, so that's a good question. So your question was if I cd into home dir.
Yeah.
So I cd into home dir. So this would actually go ahead and access that directory inode, right? For home John and nothing else, right? Even though it looks like this path. So within here is going to be all of the entries of that directory, and it's still that directory. So like this path here isn't really a real path, right? So you asked if I do cd dot dot. So if I do cd dot dot, where do you think I'm going to end up?
In home.
Yeah. Yeah, and why would I end up in home? Because that's in my directory, dot dot refers to that inode. And let's see, so if I do that, yeah, but the path, I'm in the right directory, but your shell keeps track of the path with the symlinks. So it's kind of lying to you a little bit. Well, it's not really lying to you. That's how you got there. So your shell keeps track of if you went there through a symlink, it will adjust the name based off that. Because
So at the time the dot dot was pointing to open office hours. It wasn't pointing like to home.
oh, wait. Oh, that was annoying. Okay, never mind. Okay, so in that case, your shell does something really weird then. Yeah, because we're in home directory. And dot dot is supposed to be, here, this number. Oops. Yeah, which is not this number. So my shell played a magic trick on me. So it didn't actually do what I wanted it to do. So my shell obviously remembered that when I CD'd into it, it was a symlink, and I wanted to go back to the symlink, not what that directory actually was. probably based off this path. So it figured it out based off how I got there and tried to fool me, and I guess it worked. Yeah.
Professor,
Yep.
how do you make your camera track you?
It's an AI camera.
Oh.
See? Ooh.
Like,
Whoa.
did you write the code for it, or does it come with it?
No, it is a one you can just buy. I guess I should stay neutral and not like advertise what it is. I can say it after. Actually, screw it. Yeah, it's an InstaLink 360, Insta360 link. So so you can see the actual physical thing move. But before I was using my iPhone, but I thought it looked like garbage. Because yeah, your iPhone uses like the wide angle lens and it looks like crap and it just digitally crops in. This one actually, you can see it move. Like that thing physically moves. But yeah, I only got this like Monday, but it seems to be pretty nice. All right, any other final questions, concerns? Or do we want to look at any last minute panics with the front page of the exam? Where did I even put it? Yeah, so front page of the exam, again, really quick, this short answer, page replacement, you probably know what that's going to be. Virtual memory, processes and threads, how they interact together. Locking center-fors, locking you can probably bet will be either deadlocks or data races. I actually forget, so I can't ruin that one. Center-fors, another threads question, just threads. That could also involve data races and deadlocks. And then file systems, which, I mean, we kind of just went through file system stuff here. You did lab 6, allegedly. So, yeah, so you should be good for that. Final last minute things. Let's see. So another good possible question. Let's see. Yeah, so here's like a style of question. If you can, I mean, we probably don't have enough time to go over it now because we only have like 3 minutes, but this is the CS 111 summer final, question 3. So this is probably closer to your threads and process question because guess what? It has both. So this creates, 4 threads, and then in each thread it forks. Anyone remember what happens when you fork within a thread? So chooses a random thread? Sorry? Yes, okay. So if your process has 4 threads and then one of the threads calls fork, that creates a new process. And then the dilemma is, okay, does that new process have 4 threads or does it have 1 or does it have whatever? So what it will do and what the guarantee is that newly created process will only have 1 thread running in it, and it is the same thread that called fork. So it's a copy of that one. So that's how they resolve that issue. The other weird thing that if you have threads with processes, so remember signals get sent to a process. So another thing you would have to contend with if you add threads is, if you send a signal to a process with 8 threads, what happens? Do they all process the signal? Does one get it? Because no one initiated it, right? So in the case of signals, the kernel just says, yeah, a random thread gets it. You have no control over who gets a signal, just one will get it and not everyone. And that's like, there's other complication, but those are the 2 main ones we care about. All right, so let us wrap up. So little anticlimactic end to the year, but hopefully the course was enjoyable. You learned stuff, and even if you didn't like the course, if you were staying in software, guess what? You will have to deal with this stuff because everything runs on an operating system. So hopefully you learn some things so you can actually optimize your program. You can make it multi-threaded. You can make it run really fast. And unlike other people that didn't take this course, your code won't have data races in it. You won't have deadlocks. Everything will go as fast as possible, and it will be great. So yeah, just remember for the final, pulling for you, we're all in this together. Oops.